At the end of the last video, we talked about the normal distribution having that property where the mean is equal to median is equal to mode, and then we also talked about the density curve having that symmetric unimodal bell-shaped property. There's actually another extremely useful property with normal distributions, and they follow what we call the 68, 95, 99.7 rule. And sometimes you might hear it called the empirical rule. Okay, so just be familiar with both bits of language. But the idea is that if we go out one standard deviation from the mean in either direction, I guess from the left standard deviation to the right standard deviation, there's 68% of the data. Okay, if we go out, two standard deviations to the left all the way to two standard deviations to the right, then that's the 95, right? And then 95% is in that range. And then if we go up 3 standard deviations mean, so, minus 3 sigma, so all the way to the left, 3 standard deviations to the left, all the way to 3 standard deviations to the right, covering 6 total standard deviations, then we have effectively all the data 99.7. Okay, and just so we see this notation with probability statements, is we can represent it as in this form. Okay, and just keep in mind percents. We don't typically, in statistics, we don't typically work with percents that often. We typically express it more in decimal form. Okay, but be flexible and use both. Now I call this a theorem because we can actually use calculus to prove it. And what you need to do is once you've taken calculus, well, actually you need calculus 2 and a little bit more. Is that you need to integrate this function with respect to x from whatever your bounds are, okay? And then you'll get these numbers popping out, okay? Technically, you have to use a Taylor series to do it, but I digress, okay? So, calculus aside, let's see how this works out on our curve, okay? This picture you will probably want to put on a cheat sheet or, have it readily accessible in your notes because you are going to use this a lot. And I mean a lot, okay? So I'm going to make a normal density curve for just a generic random variable x that has a mean of mu and standard deviation sigma. Okay, so mean mu, and then if I go out to that first bending spot, I'm going to call it right there. So I'm going to kind of go down. I'm going to call this mu plus the standard deviation, and then go to its symmetric counterpart over here. Call this mu minus sigma. So I'm going now subtracting the standard deviation, whatever it might be, and then I'm just going to kind of continue to go out in a symmetric manner. So here we go. I'm going to call this mu minus 2 sigma, and then down here, I'm going to call this mu minus 3 sigma, and here mu plus 3 sigma. Okay, so now what we know is that within one standard deviation, right, there is 68% of the data, okay? But we also know that everything is symmetric in a normal distribution, so that 68% is split between the two sections that make up, or that it makes up. So that means this section is 34% and this is 34%, okay? These numbers are kind of useful, okay? I recommend jotting them down. We also know that within 2 standard deviations, right, from here to over here, there's 95% of the data, okay? So that, again, you have to figure out how much is in each of these spots over here. You need to take, 95 minus 68, and then divide that in half. It ends up being 13.5% in each of these pieces. 27% split in 2. All right, and then we also know that within 3 standard deviations of the mean, there's 99.7%. Okay, and again, doing the math, so you have to take the 4.7% and split it in 2, you get 2.35% of the area, or 2.35% of the population or observations are in between 2 and 3 standard deviations away. And then everything has to add to 1, so then take the remaining and split it. So this ends up being 0.15%. Okay, so in other words, if you have some quantity that is following a normal distribution, it's very unlikely that you get anything that's more than 3 standard deviations from the mean. Okay, so this curve is going to help us immensely. Okay, so let's see an example. Okay, so so digit ratio is actually known to be a normally distributed quantity, and what it is it's the ratio of the pointer finger length. So kind of if you include the thumb as your first digit, it would be the second digit divided by the fourth digit, the length of your ring finger. Okay, and it's actually a normally distributed quantity, and then in males at least, the mean ratio is 0.95 with a standard deviation of 0.03. Okay, and it is unitless because it is a ratio of two things. So we want to let D represent the random variable. Okay, and then we have, several questions to answer related to it. Before you tackle the question, what I always recommend is take the information and represent it in picture form. So we know that D follows a normal distribution, okay, using our language, normal distribution with mean 0.95 and standard deviation 0.03. Okay, so now what I'm going to do is make a normal curve. Okay, it is just a sketch. Okay, and I'm going to do my best to label things. So I know right in the middle is going to go the mean. And then I want to replicate that process that I did up here. So count out by standard deviations and include the percents in each of the sections just for my reference later on. Okay, so I'm going to encourage you to pause the video, try it out, and when you're ready, resume the video. So I have mine all labeled, okay? So you can see I counted, I added, as I went this way, I added the standard deviation every single time. And then as I went to the left, I subtracted the standard deviation, okay? So anyway, there we go. Part A, what is the probability? Okay, so this is, there's notation, right? When I'm asked for a probability, I should write a probability statement. Probability that a male's digit ratio, that's our random variable D, is less than 0.98. Okay, so now this is why I like the diagram, because I can just go up there and say, oh, okay, 0.98 is right here, and then I want to find when D is less than that. So I can either take out my calculator or just say, okay, well, I know from the mean, that's 50% to the left, and then I add 0.34, I get 0.84. Okay. Part B, what is the probability statement that a male's digit ratio is at least 0.98? So it's bigger than 0.89, sorry, rather. I said that wrong. But no more than 1.04. Okay, so I'm looking from here up to there now. Okay, so I would have to add everything up. So let's see, that's from 0.89 to 1.01, right? That is 95% because it's, 2 standard deviations from the mean. And then I need to tack on that 0.234. So let's see, 95 plus 0.2, let's see, so this is going to be 0.9735. Okay, easy enough, right? All right, part C, what is the largest digit ratio for the smallest 16% of male digit ratios? Oh man, okay, things changed. I'm not being asked for a probability, but I am given this probability, 0.16. Okay, but now I need to think, okay, where is this on my curve? Okay, the smallest 16%. Smallest, that means smaller value, right? So, okay, I'm just going to start from the left. And so I'm looking for an area that is 0.16. I don't have it, right? But if I kind of start, I say, okay, well, less than 0.86 is this 0.0015. If I tack that on, or if I tack 2.035 onto that, that's up to this point, it's, 0.025. So 2.5%. And then if I tack on the 13.5, then I'm at 16%, right? or 0.16. So this one, there isn't a whole lot of work I can show. I just have to say that the largest digit ratio here is 0.92, okay? And if you need to, you could add up the error, or you could add up those pieces and show your work that way, but I would just probably show or list the answer. All right, and then almost all, 99.7% of male digit ratios are between what two digit ratios? I remember that this is from, so 99.7, that's from minus, or the mean minus 3 standard deviation all the way up until the mean plus 3 standard deviation. So that's just going to be, in this context, 0.86 and 1.04. Okay, so just keep in mind when you're working with these exercises, if it's asking for a probability, always include the statement. If it's asking for a value from the population, then just kind of list the value. Technically, what you would do here is you could write a probability statement. It would be probability that D is less than 0.16 is equal to 0.92. That's a probability statement that you could do. For this one, similarly, you would do P of, oh, I'm sorry, I have these backwards. Try that again. P of D is less than 0.92 is less than 0.16. Similarly, for this one, it would be P of 0.86 less than D less than 1.04 is 0.997. Okay, so you could write the probability statement that way, just knowing that the value that you get goes outside. But nevertheless, the important thing is find the values if you're being asked for a value, and for probabilities, make sure to use the normal density curve to your advantages and the empirical rule that it carries with it.